I wanted to talk about how we solve word problems in chemistry and really get solid with dimensional analysis in particular. There's a couple of great videos by Tyler DeWitt. The book does a pretty good job explaining things. I have some slight tweaks on that, but certainly I don't disagree with anything they do. So to start off, we have this problem here. The density of aluminum is 2.7 grams per cubic centimeter. And our question is to find the volume occupied by 10 grams. So again, 10 grams, 2.7 grams per cubic centimeter, what is the volume? So we have two ways that we might approach this. One would be using kind of an algebraic approach, which involves using the equation for density equals mass over volume, recognizing what we want in this problem is the volume, so we would rearrange that and have that volume equals, substitute around here, mass over the density equals my mass of 10 grams divided by the density of 2.7 grams per centimeter cubed equals, punch buttons in calculator, 3.70 centimeters cubed. And we should pay attention to the units here. Grams cancel. I have 1 over cubic centimeters, which gives me cubic centimeters. All right, this is really useful and important when we have an established equation or a formula that we are using. So the area of a circle being pi r squared, the density is mass over volume. I don't know, there's a whole host of other ones. More generally, though, we're better served using a pre-algebra approach. And this is our dimensional analysis, or unit conversions, or whatever else. And so what we're doing here is just doing sequential conversions. In this case, it's one step, but nonetheless, it's a good starting point. Okay, so I'm starting with a knowledge of mass, or grams, and I'm going to go through some process, maybe it's a couple of steps, maybe it's just one, to come up with a volume, cubic centimeters. So this is what I would refer to as a roadmap. It's how I'm going someplace. I'm getting directions here, but I'm not worried about actually showing conversion factors here or even doing any calculations. All right, once I've established from the word problem what my process will be, then I actually execute it. So I'm going to start with my 10 grams, and then I'm going to do a conversion that lets me get towards where I want to go. So I'm going to have grams in the denominator so that it cancels, and if I can do it in one step, great, centimeters in the top. And my conversion factor here is that I have 2.770 grams per cubic centimeter. And when I do my conversion here, I get my centimeters cubed, so I'm focusing on the units first, and then when I do the calculation, I get that same 3.70. Okay, so different approaches. If we have something like some of the gas laws that we see in Chapter 8, we tend to use a more algebraic approach, but for most of the problems we see in, say, Chapter 2, and then when we do a lot of other conversions through most of the textbook, this approach is much better. So let's do some more complicated examples of that. All right, a fairly simple problem that is going to use this dimensional analysis approach would be this sort of conversion, calculating how many miles 135 inches would be. Most of us would sort of shoot from the hip and say, oh, let's see, I'd go 135 divided by 12, and then whatever that number is divided by the 5280, and sort of do it reflexively, just because we know magnitudes of things. And my view is that we want to move away from doing it in that kind of instinctive way and rely on a very scripted, engineered solution that I call a roadmap. And the reason for that is as we move forward and we start talking about things that are less familiar to us, either chemistry things or other science things, we want to have a process that we're very comfortable with rather than being able to manipulate numbers that we already have a pretty good understanding of. So with this problem, similar to what I started with, we want to have this word problem turned into something that's the start of a math problem. And again, I call that a roadmap. And the roadmap in this one, very, very simply, is I'm starting with inches and I'm going to miles. And by the way, if you have a problem you're not familiar with, mark it up, really be sure what's going on here. So what I'm going to try to do then is I'm going to go from inches through some process to get to miles. Okay, and I might just look at the word problem and say, I don't know how I'm going to do it, but I know where I'm starting, I know where I'm ending. And hopefully there's a context or familiarity with a problem that we can replace these arrows with something more specific. So I might recognize, oh, I can't go from inches to miles directly because I just don't know that, but I do know something about feet for both of them, and we have some conversion factors over here that would be available to us. All right, so with this one, I'm probably going to go inches to feet to miles. So this, again, is my roadmap. This first one I'd also call a roadmap, but really that's me just kind of defining what the problem is in my mind. Okay, once I've got that, then I'm going to do a solution. And my solution here is going to be actually taking the problem, 135 inches, replacing this arrow with a conversion factor. Okay, so the conversion factor that's in the DeWitt videos that the book talks about, in my roadmap, that arrow is the conversion factor. So here I'm going to put my inches in the denominator so that it cancels, and my numerator is what I'm going to. So if I stopped right here, I'd have feet, and that's where I am. Now my roadmap says keep going, convert feet to miles. So to do that, I have that there are, I think, 5,280 feet in 1 mile. And again, units cancel, I'm left with miles. Now in a assessment situation, a test or a quiz, whatever, if I saw this and saw the miles there and it was a totally wrong answer, I would still want to give most of the credit for it. If this was a 10-point problem and you just goofed up some sort of arithmetic part, you'd still get 80 or 90% to show that this had happened and that the units worked right. If we can do this part, punching buttons in the calculator is easy. So what we want to do is avoid hastily punching buttons and just trying to get a number. Rather, we want to make sure that the process is right, and we'll just have confidence that we can actually see the buttons and hit the right buttons on the calculator. All right, so that's that guy. And so we got 2.13 times 10 to the minus 3 miles, which of course we could have written as what, 0.00213 miles. Units important, number hopefully goes with the turf. The process is really what's key. All right, let's look at one that's a little bit more difficult. We're going to change miles per hour. So we've got 60 miles per hour. We want to convert that to meters per second. So again, a road map here, we're going from miles per hour through some process to get to meters per second. And M's are funny. We got M's all over the place. Meters, minutes, miles. There's probably other ones. So we got to be a little careful with our abbreviations here. And with miles, I'll just leave it as miles rather than try to shorten it. Okay, so more specifically, how do I do that? And I want to recognize that I have a whole bunch of conversions. Some of them are going to apply to the numerator. I've got distance on the top, distance on the top on there. And I've got time in the denominator from both starting and ending. So the key to these roadmaps and the actual calculation is that we do things one at a time, one step at a time. So I'm going to go miles per hour. And I need to be able to get to meters. Now, maybe I have a conversion. Let's go from miles to kilometers to meters. Maybe there's a mile to meter conversion directly. But if I'm sticking with the stuff here, just to make this more of a challenging problem, I see that my miles, I'm going to go to feet, feet to inches, inches to centimeters, and then metric conversions are assumed that we know. That's why metric's great. It's easy, right? And then the time, of course, I can do fairly directly with those last two things. So from miles, and using what's on my chart there, I'll go to feet per hour. Then I'll go to inches per hour. And I'll go to centimeters per hour, meters per hour. Let's see, now I want to look at the denominator, so I'll go meters per minute, meters per second. So that is my roadmap. I can do any one of those conversions with the information that's here and metric. And again, I recognize that there might be access to conversion factors that speed that up, but we want to be able to do this process. So like snapping together pieces of a jigsaw puzzle. Okay, the actual calculation here, I've got 60 miles per hour. To do that first conversion, just like the last example, this arrow is going to turn miles into feet. So the miles goes in the denominator, and the conversion to feet in the numerator. Next I want to go feet to inches. So again, 1 foot, denominator, 12 inches, numerator. Next I've got inches to centimeters, so I have that 1 inch is 2.54 centimeters. I have that 100 centimeters is 1 meter. It's not on the table there, but we should know those metric ones. Okay, now we got to pay attention to one little tricky thing. Hours is in the denominator here, so it has to go in the numerator here. 1 hour is 60 minutes. And out of space, but 1 minute is 60 seconds. Okay, important part of the process is making sure I did it right, and I'll see that by seeing that my units work out. So my miles cancel, my feet cancel, my inches cancel, my centimeters cancel, and I'm left with units of meters. And then looking at the time, my hours cancel, my hours cancel, my minutes cancel, my minutes cancel. So my answer will give me something in meters per second. All right, so there's our problem statement. I recommend that you pause the video if you're actively working on this and give yourself a couple of minutes to try to work this out. Do a roadmap and then calculate an actual answer. Ask yourself if it makes sense, and then watch the rest of the video. All right. All right, let's do one more. This one, we're going to calculate the mass of 2 cubic feet of water. So we know that the density of water is 1 gram per cubic centimeter. Our question is finding the number of pounds that 2 cubic feet of water occupy. So as before, first thing to do is make sure we understand this problem, and we're going to go from cubic feet of water to pounds, again, of water. And this is going to be a multiple steps, so maybe I should have strung out a whole bunch of arrows here. All right, doing this problem, again, focusing on where to start is difficult, I think, a lot of times. Even for me, I might stumble around. But I'm given this piece of information, so that's probably going to be my start. And again, from the problem, we know what that is. So I'm going to go from feet cubed, and I need to somehow go from a volume to a mass, which is going to be a density. So and my density, of course, is this up here, the grams per cubic centimeter. So that suggests to me I need to go from cubic feet to cubic centimeters, and then that'll be my conversion to a mass. And eventually I'll convert that to weight, really, but anyway, the weight in pounds. Okay, so cubic feet, I'm going to go to cubic inches to cubic centimeters to grams, and grams to pounds. So that is my roadmap. All right, actually executing this, I have that there's 2 cubic feet know that 1 foot is 12 inches, but notice this is cubic feet, this is just feet. And so I can't just put a cube here, I have to cube the whole thing. And the important part here is that means I'm cubing the 12 as well, right? I'm doing this process of multiplying by 12 inches over a foot 3 times. All right, once I've done that, I'll have cubic inches here. I know that 1 inch from my table is 2.54 centimeters. Same again, I need to cube that. At this point I've got cubic centimeters. That lets me go to, oops, not an arrow there. I'm going to recognize that 1 centimeter cubed is 1 gram. And lastly, that there are 454 grams in 1 pound. Okay, so I've set that all up. I want to double check that the units actually work, and I might do this as a, let me just do another color here. Okay, so I've distributed that cube across all the pieces of the term. All right, so my cubic feet cancel, my cubic inches cancel, my cubic centimeters cancel, my grams cancel. So I started with cubic feet, I've ended with pounds. That's what I want. There's my pounds, and it's 124.7, rounded 125 pounds. Okay. All right, one last problem. This one I want to focus on percentages. So if we have a sample of seawater, it's 3.5% salt by mass, and the seawater has a density of 1.02 grams per mil. And our question is, how many liters of seawater is needed to obtain 50 grams of sodium chloride? Okay, so again, we might want to look at this problem and ask ourselves, what are we given and what are we trying to find, do the roadmap, etc. So just like the last problem, go ahead and pause the video, try to work this out, and then proceed. And if you need a little help, maybe watch a part of it, get the roadmap, and then again go through some active processes here. Okay, go to it. All right, so again, we're trying to get 50 grams. So even though that's the end of the problem, that's what we obtain from the experiment, if you will, that's really where we start our calculation. So my roadmap here would be grams of sodium chloride. Oh, forgot a very important step. When we see percentages, a really good thing to do is turn that into something that's more useful for our calculation. So I'm just going to run that down here and say that that 3.5% means 3.5 grams of sodium chloride per 100 grams of seawater. Okay, that's my conversion factor. And notice a percentage, it has grams over grams, but it's not exactly the same. It's grams of sodium chloride per grams of seawater. And those units are important for ultimately how we solve the problem. So grams of sodium chloride, I'm going to go to grams of seawater. From grams of seawater, I'll go to mils of seawater, and from mils of seawater to liters of seawater. So that is my roadmap. And I'm guessing this problem looks difficult. A lot of people throw their hands up. If it was a quiz or test question, results might not be great, but it's really not that many steps. Okay, actually the calculation, I have my 50 grams. What did I say, 2 sig figs? Somewhere in there, 50 grams of sodium chloride, salt. To convert that to grams of seawater, I use the percentage. There's 3.5 grams of sodium chloride. Let's write that a little nicer. 3.5 grams of sodium chloride for every 100 grams of seawater. I want to go from grams to volume, that's my density. So I have that 1.02 grams of seawater is 1 mil of seawater, and the problem wanted the answer in liters, so I have 1,000 mils is 1 liter. Go through and check the units. My grams of sodium chloride cancels my grams of sodium chloride. I don't want to cancel grams of seawater with grams of sodium chloride, right? I got to be specific about those units. This process eliminates that guesswork of, oh, do I multiply by the percentage or divide by the percentage? All right, so my grams of seawater at this step converts to mils of seawater, and of course my mils converts to liter in that last one. I'm left with liters, and it's 1.40 liters. All right, that's it. These sorts of problems, this dimensional analysis, roadmap driven, turn a word problem into a math or an arithmetic problem, very, very important. It's probably the most important skill, certainly math skill, for this class or for any beginning science class. So really work on those problems, especially the latter part of chapter 2, but then we'll see it in most of the rest of the chapters. So again, can't do too much of this.